Thus far, we have looked at situations of members that were axially loaded that had either the entire member being subjected to the constant axial force, or at least they were discrete sections that were. And now we're going to look at one where we have a continuously varying set of conditions. And even though the member is prismatic in that it has it's uniform in both its cross-sectional properties as well as its mechanical properties and its also its density, what's not going to be constant is the axial force, because the only applied force is the weight. Right? So I already did a preliminary calculation on the area. It's 2 1/4 pi square inches, which is a little over 7 square inches. That's a lot of cross-sectional area, especially for a member that's only 3 foot long. But let's see it. Steel is pretty heavy, pretty dense. And let's just take a guess at what we think this axial displacement would be, just due to its own weight. Right now, with a uniform situation, you might say, hey, the center of mass is right about here in the middle, and if this became a weightless rod within just a force applied there, we could estimate delta as being that weight times the length at the midpoint. That would be the portion that would elongate only half of it over AE, and that would be WL over 2AE. That's kind of interesting. The basic model would be the axial force times length over AE. This suggests that it might be half that. I'm not going to work through the numbers here. That already gave us a model for guessing. It's going to turn out to be a really good model, but only under very special kinds of conditions. Let's see what happens here to do this in a more appropriate kind of fashion. And that is, we got to go all the way back now to first principles, and that is our axial elongation is going to be equal to the sum of all of the elongations that are happening along the length of the member. Right? So if we go down into a little piece, there's our little dx, and let's set up our coordinate system that x, I know that's vertical and you probably want y, but I'm still going to use x, just turn it 90 degrees. Right? And that's the only dimension that matters, it's one dimension. And okay, so d delta, all right, wait a minute, strain, that's d delta over dx, so therefore d delta is equal to strain times dx. All right, we can drop that right in. And we've not lost anything in any sort of approximation so far. And if elastic, then stress is going to be equal to E epsilon. So strain, of course, is equal to sigma over E. Right? A little glimmer of interesting hope here. So that's sigma over E times dx. Now, if it's homogeneous, then, alright, the E can pop out, so that's an if. That'd be 1 over E. And, of course, stress is going to be sigma is equal to the axial force over the cross-section along the length, integrating from 0 to L. Well, that's interesting. Now, normally we'd pop that out because axial force was constant, cross-sectional area is constant. But if neither one of those is constant, they have to stay in, and we have to come up with a function as of the position of x. Well, let's not screw around with that too much, meaning, all right, A is constant. When I say don't let's screw around with it, well, let's deal with the constants that are really there. So the rigidity of the cross-section is EA. That gets pulled out because it's not a function of x, and we just have then n times dx. But the axial force is now going to be function of the position. So let's go look at what that might be here. If we go down to x, that's where we're at here. The positioning is cutting down at x. If I hadn't put this silly little box here, I could have drawn that all the way down and just cut it off right here. But we're taking that lower half, and that lower half then has an axial force. It's a function of x. And what's left over, well, we got the self-weight of this little piece. Now that weight is going to be what? How much? It's a function of x. Well, that's Interesting. All right, so how much of this do we have? Well, we've got a leftover piece here. That's L minus X. It's of cross-sectional area A, so the volume is going to be equal to L minus X times A, and A is a constant. And so that makes this equal to the unit weight, because that's weight per volume, times L minus X times A. There we go. I think we've got it, because now simple equilibrium, those two are going to be equal to each other. And so now we've got 1 over EA, integral from 0 to L, of gamma times L minus X times A times dx. Well, gamma and A are constant, so we get gamma A coming out. We have EA here. I don't want to cancel that out just quite yet, for a reason that will become more apparent at the end. We could, though, if we really want to simplify. And we'll have the integral from 0 to L of L minus X times dx. And so gamma A over EA, and now we get to see me integrate. That will be Lx minus x squared over 2, integrated from 0 to L. The 0 will go out. That's nice. We'll have an L squared minus L squared over 2, which will ultimately be gamma A L squared over 2A E. Isn't that interesting? Because gamma AL is the weight, total weight, right? Total weight back up in here, W equals the mass, the unit weight times the total volume. And so that would be equal to W times L over 2AE. How about that? That was actually exactly equal to my little approximation. Hey, that only happened because of the uniqueness that we have. A constant A, constant E, constant unit weight. If any of those parameters vary, or the function of x, then that all has to get put in here, and the equivalent effective displacement is not going to be found by putting the weight here. But it would be kind of interesting to ask, well, if that's the case, as long as we have uniform density, would it be just at the center of mass, or wherever that is at? Interesting question to try to work out in a more broad kind of way. But nonetheless, this is the beginnings of how you handle non-uniform situations that are continuously variable. Sometimes you can do it like here, where it's tractable. You can easily do this. Sometimes the full integration of these things are not tractable. You have to use numerical approaches to evaluate those integrals.